All right, let's dive into one of the biggest stories in chemistry. We're going to take a trip back in time to see how our idea of the atom evolved from just a tiny, solid ball into the complex model we study today. It's a really fundamental concept. And hey, for those of you gearing up for your exams, remember that active learning is everything. You can always check your understanding over at mqspenia.com. But first, let's build that foundation together.
Yeah, of course they do. But listen, these aren't just names you have to memorize for a test. Think of them as pioneers, right? Each one added a crucial piece to this giant puzzle of the atom. It's less like a boring list and more like a relay race, where each scientist grabbed the baton of knowledge and ran with it, building on and sometimes totally flipping what the person before them thought.
I know, it can feel really tricky, and that's usually because it's not just one idea, but a whole series of them. The secret isn't just memorizing facts, it's understanding the story, why each new model had to be invented. A super common mistake I see is students trying to learn each model separately. We're going to connect the dots right from the very beginning.
Okay, let's untangle this. Our story kicks off with John Dalton, way back in the early 1800s. He basically said atoms were these tiny, solid, unbreakable spheres. Super simple. But then, in 1897, J.J. Thomson discovers the electron, this little negatively charged particle. And boom, suddenly the atom wasn't unbreakable anymore. This led him to his plum pudding model. Just picture a bun of positive charge with these negative electrons stuck in it, kind of like raisins.
And this is where the details really start to matter. See, Thomson's model was a huge step up, but it was just an idea. So Ernest Rutherford decided to put it to the test with his now famous gold foil experiment. He literally shot these tiny alpha particles at a super thin sheet of gold foil, and he expected them all to just zip right through. Well, most of them did, but some of them were deflected, and a few, get this, bounced straight back. This was absolutely shocking. It was, and I quote, like firing a cannonball at a piece of tissue paper and having it come back and hit you.
So what on earth did that crazy result mean? It meant the whole plum pudding idea had to be wrong. There's no way those particles would bounce back unless they hit something really small, really dense, and positively charged. And just like that, Rutherford gave us the nuclear model. A tiny, positive nucleus right in the center with electrons orbiting it, and the rest of the atom was, well, mostly empty space. A massive, massive breakthrough.
But, even Rutherford's model had a little problem. According to physics at the time, those orbiting electrons should have been losing energy and spiraling straight into the nucleus, causing the whole atom to collapse. This is where Niels Bohr comes in. He proposed that electrons could only exist in specific energy levels or shells. They could jump between these shells, but they couldn't just spiral into oblivion. It was a brilliant idea that perfectly explained a lot of other observations and made the atom stable. So there you have it, from a solid ball to plum pudding to a mini solar system to one with stable shells. That's the story.
Okay, now that we've walked through the whole story, how do you make sure you lock this in for your exams? Well, you have to move from just passively listening to me to actively using the information. And that's where a tool that's built for this kind of targeted practice like MCQ SPM becomes your best friend.
So why is this so important? Well, think about it. Exam questions on this topic love to ask you to compare the models or to explain the experiment that led to the change. For instance, a classic question is, explain why Rutherford's experiment disproved the Thomson model. Just reading your notes over and over isn't going to prepare you for that as well as actually trying to answer the question yourself. And getting started with this kind of practice is super simple. If you've got your phone with you right now, just open your camera and scan the QR code you see on the screen. It'll take you exactly where you need to go.
And hey, if you're on a computer or would just rather type it in, you can go straight to the website www.mcqpm.com. The whole idea is to make getting quality practice as easy and as fast as possible.
The last thing you want is to waste precious study time with some complicated sign-up process. This is designed to be super quick, so you can jump right into what actually matters, testing what you know.
It's really just 3 easy steps. Once you're on the site, just click Login, use your Google account to connect, and you're in. That's it. You can immediately start looking for questions on atomic structure and see how well you've really grasped the concepts we just went over.
So let's tie this back to our topic. Active learning forces your brain to recall the specific differences between, say, the Rutherford and Bohr models. Targeted practice lets you zero in on this specific chapter until you've got it down. And the result? It's not just knowing the material, it's having the confidence that you can handle any question they throw at you under exam pressure. This right here is the absolute core philosophy of effective studying. Listening to me explain it gives you the story and the framework, but testing yourself is how you make that knowledge truly, truly yours. It's how you find those tiny little gaps in your understanding before the exam finds them for you.
So you see, the journey of the atom is a story of turning confusion into clarity, one discovery after another. And your own study journey should be exactly the same. When you understand the why behind each model, and then you actively test that understanding, you transform that feeling of being overwhelmed into real, solid confidence.
So you've got the story of how the atomic model grew up. The next step is all on you. It's time to challenge yourself. Are you ready to apply what you've learned, pinpoint your strengths, and turn this tricky topic into one of your absolute best?